Hello, we will now be presenting our tolerancing scenario project on a jewelry box for ME110 or manufacturing processes at San Jose State. My name is Alexander Wiley and I'm alongside with Elijah Sanchez, Megan Kiefer, Elizabeth Brimberg, and Matthew Abdallah. Now to introduce, our focus for our jewelry box assembly will focus on the analysis of the assembly pertaining to the tolerance between its jointed pieces. Quick details, this is a conceptual design based on web influence and does not contain fasteners at all. Every part is bonded via dovetail joints. Let's actually get into those. For dovetail joints, these are used for woodworking mostly and known for its strength and resistance to be pulled apart. This design dates back to ancient history, as civilizations in India, Egypt, and Babylon have utilized it for their woodwork goods and even for buildings. Types full, half, and sliding, and are utilized in modern times in furniture.
Now we'll transition to talking about requirements. First, the use requirements. The box must be easy to open and close with compartments to organize various jewelry types. Surfaces should be smooth to prevent injury to users or to jewelry. Materials need to be durable, resist wear, and the design must be aesthetically pleasing. Next, for the assembly requirements, dovetail joints should fit seamlessly without adjustments, and the process of assembly must be intuitive. The wood grain should be aligned to prevent warping. Parts should be replaceable, and the material must resist splitting. Finally, the wrist requirements. The dovetail joints need to handle loading without breaking, and edges should be rounded to prevent injury. Hinges must endure repeated use, and the base must be stable to avoid tipping even with the drawers open.
Our main concerns for the assembly are the failure of fitment in a worst-case tolerance scenario, consideration of expansion due to environmental factors, and the order of assembly. For our assembly drawing, we have the dimensions of the drawers called out to ensure proper fitment and functioning of our drawer. For the exploded view, we have the order of assembly called out, with the middle divide being first, and the drawer side slotting into that, and the drawer back also slotting into the middle divide. Then we have the top and bottom lids slotting into the sides and back into their dovetails and pins respectively. And then finally we have the drawers slotting into the main frame, fitting comfortably into their areas.
Now, with a focus on the parts, we will now first focus on the top/bottom pieces. Here is the drawing and the image of the model. Today, we will focus on its tolerance zones. In regards to tolerance zones, we will specifically focus on the teeth. The teeth will be at an angle of 50 degrees and be within a tolerance of 10 angstroms or 17 hundredths of a degree for proper fitting. The top bottom piece for the assembly is the foundation of the drawer frame. We are referencing these tolerances from Valley Tools custom cutters, and these angle tolerance calculations will be provided, and we're going off the standard from Harvey Tools as well.
For the back piece of the drawer, the aim is to bring together the rest of the assembly. In order to do this, we need to ensure that the overall shape of the back piece is relatively square so that the mating surfaces of other components won't interfere with each other. We call out flatness on datum A so that during inspection this will be our main reference surface to other geometric controls. We call out perpendicularity on datum B in order to control the overall shape of the piece, and then call out parallelism with the opposite side in order to lock down the squareness of the piece. In the slot of the back piece, we need this mating surface to be perpendicular to datum B, not only to control the relative angle it makes with the datum, but also the flatness of that surface to some extent. There are 4 holes in the back piece for press-fit pins to hold the assembly together, and these holes have very tight tolerances to ensure interference fitment. We lock down the position of these holes with a position callout with the least material condition. This is because any bigger hole than the maximum tolerance diameter risks splitting the wood on the sides of the hole if its position is allowed to change. So to prevent splitting, the bigger the hole is, the more strict we need to make this position tolerance.
For our jewelry box, the main focus is setting the fit with our components for the square design. Detail K shows the dovetail cutouts, which are defined by angularity with respect to the first datum, as well as a tight tolerance to ensure press fit based off the reference material dimensions that we found. In the main drawing, the slots for the center divide have been defined using parallelism and perpendicularity to ensure squareness, as well as a continuous width, which will allow for continuity and levelness of the slots that support the drawers later. In conclusion, we were able to develop drawings which met our assembly goals for effective use as a jewelry box. Thank you for listening to our presentation, and here are the references we used for our project.